Hello everybody. Today we will continue the polymer classifications and we will pass to the third polymer classification category, which is based on chain architecture. This category on itself is divided into four parts. We have the linear polymers, we have the branched polymers, the cross-linked ones, and the network. What's the difference between these different chain architectures? When we talk about linear polymers, the monomers are joined together in a linear manner, forming a long straight chain. While in branched polymers, some monomers are joined as branches of different lengths on the polymer backbone. The polymer backbone is the principal polymer chain, and these are the branches. So we have this category of polymers named branched polymers. If the monomer units are joined in multiple chains and form interconnections between chains, these interconnections are named cross-links. Usually they are covalent bonds. Thus, cross-linked polymers are made. When the cross-linked polymer includes plentiful interconnections between chains in 3D, so a network polymer is formed. So now I will give you an example for each kind of these polymers according to their architecture. As linear polymers, we have many examples. In fact, when the polymers are in linear form, these polymer chains can pack together and lead to high density materials. For example, high density polyethylene, polyvinyl chloride, nylon, cotton. I want to repeat, as the polymer chains are linear, so here we can find many polymer chains which can pack together, leading to high density materials. If I want to consider the high density polyethylene, do you remember we have repetitive unit? Here we have the ethylene repetitive unit, and as you remember, we have this number N. It's the number of monomer repetitive unit in the polymer chain. As this number N increases, so the number of monomer units increases, and thus the chain length increases. Also, the molecular weight of the polymer increases also. So, for the same polymer, for example, the high density polyethylene, we can use it as trash bags, as bottles, and if we increase the chain length, we can go to different kind of garbage boxes, big bottles, also pipes. So this small number of N influences the application of the polymer used. All these examples are of high density polyethylene, but of different chain length and of different mass. Please check your shampoo bottles at home, your ketchup bottles, almost all materials that you have. You should now start having the curiosity of which polymer they are formed. So you should check each polymer materials that you can find around you at home to read or to know of which polymer is made. Now, if you continue increasing this number N, and thus the chain length can go from 2 to 6 million repetitive units. So we can use this high density polyethylene. It's becoming ultra high molecular weight polyethylene, as it could be used for gears, for joint replacements, and also for military helmet. Now, if you consider the second category of polymers classified according to their architecture, we have the branched polymers. And here we talk about low density polymers, for example, low density polyethylene. Because if you look here, we have the backbone chain and we have the branches. Because of these branches, these polymer chains cannot easily pack together. Thus, they are of low density, and they are used in plastic bags, for example, for packaging plastics, for food as wrapping films, or for healthcare as dropper bottles, where we can control the quantity of medicine given, etc., etc. Also here, for the same polymer of low density polyethylene, the variation of number N leads to the variation of chain length and also on the density of this material and thus on its application. Now the third kind is the cross-linked polymers. As I said, we have the polymer chains which are connected between each others through covalent bonds named cross-links. These covalent bonds maintain the polymer chains connected together. If I give an example of cross-linked, we have, for example, the starch. As you probably know, the starch is formed of amylose and amylopectin, which are natural polysaccharides polymers. So while we are cooking the starch, the amylose melt and it's leaked out from the pasta, for example, spaghetti, potato, etc., etc. So if we consider now the example of spaghetti, while cooking the spaghetti, as I said, the amylose is leaked out, and when it's cooled, the polymer amylose chains, imagine these are the amylose starch chains leaked out from the spaghetti. So while cooling, these polymer chains will start to become closer to each others and connected through cross-links, covalent bond. So that's why the spaghetti are tangled together. So what we can do to avoid that spaghetti get tangled together? So you have to propose solutions and to send it to me via Google Classroom with explanation what we can do to avoid the formation of cross links between the spaghetti. Okay. Now, if I continue also, as I said before, if the number of cross links increases, we obtain network, and this is the fourth category of chain architecture polymers. Example of this category are what we name bakelite, melamine, Kevlar, and epoxy. الميلامين هول كل الصحون البلاستيك القياسي اللي بتشوفوهم عن ماما بتستعملوهم بالبيت. الباكليت مثل الأساور تبع الصبايا اللي بنسميهم بالعربي عظم، والزرار اللي بنسميهم عظم. We have also the Kevlar, which is important polymer used for example البروتكشن بالحرب بالارمي دروعة. وهول البوليمرز عندي different polymer chains connected together via hydrogen bonds and also covalent bonds أكيد. Another example of network, we have the hydrogels. The hydrogels are very important polymers. They are three-dimensional networks of hydrophilic polymers. Hydrophilic, so that's mean they can swell in water. Swell, not dissolve. So both solid-like and liquid-like properties these hydrogels have. The ability of hydrogel to hold significant amount of water means the polymer chains should contain specific functional groups, giving them the ability to make hydrogen bonds with water and to maintain or to hold significant amount of water. Example جل اللي بتستعملوه الشباب والصبايا، احنا بنعرف نحط small quantity of this gel وما نحط لها مي، so هذا gel will swell and we can use it to fix our hair. Example, very important also example of the hydrogels polymers is in the drug delivery systems. In fact, these hydrogels are very important because we can control them with different stimuli. So they are stimuli responsive drug delivery. So we can influence these materials, these polymers materials, which are named smart materials, by variation of pH, by variation of the temperature, by different factors. So these polymers, why they are very important? Because in fact, we can take the polymer and we can put the drug inside this gel polymer. So this polymer can swell or collapse. So by swelling, by modifying the pH, the polymer chains imbibe water and swell, and thus the drug are released out from the gel. Or instead of swelling, the gel can collapse by changing the temperature. So by collapsing also, the polymer chain get closer to each other and the drugs are also released from the initial gel. The benefits of this controlled drug delivery are they are more effective therapies, and they are much used now for the cancer treatments. So we can send the drug inside such hydrogel polymers, and we can influence them in a specific way, in a specific place in our body. يعني محل ما عنا السيلز ما يصير في عنا treatment for example بيصير في release للدراج. So هيدا صار الدراج destinated محل ما لازم يصير فيه treatment، مش everywhere in our body. So هذا very very important factor or very important application of polymer networks. Another example about polymer network is the food gel formation. In fact, if I consider the cooking of potato or chicken, as you know, potato contains starch, which is natural polysaccharide polymer, and the chicken contains proteins. So after cooking potato or chicken and cooling, have you ever observed the thick layer formed at the top of cooking pot? In fact, this layer, if you touch this layer at the top of the cooking pot, بتلاقوها viscous. Okay, this viscous layer is a gel, and here we have food gel formation. How we have formation of this gel and the polymer network? In fact, while cooking both starch or chicken, we have polymer chains which are leaked out in the cooking pot in the water, and after cooling, the polymer chains start to become closer to each other. While they are closer to each other, we have the possibility of formation of interactions between the polymer chains, interconnection. These interconnections are crosslinks. And as we know, if we have an important number of these cross-linkings, we have formation of network polymer. And the gel is an example, food gel formation is an example of polymer network. We have here the polymer chains, which are close to each others and which are connected by cross links, and also we have water molecules inside these holes connected. Okay, here we have formation of gel. هون لما نحن نطبخ الدجاج او البطاطا او الفاصوليا ونتركهم ليسقعوا، نجي بنشوف على التوب للبوت بنلاقي عندي هيدي الجلي layer. So هيدي الجلي layer هي formed من البوليمر chains leaked in the solution اللي هن while cooking قربوا على بعضهم وعملوا interconnections وعملوا هالcross links وعملوا imbibing للwater inside وصار عندي formation of gel وبالنهاية polymer network. Now if I ask you another question, have you asked yourself why jello, you know الجيلو اللي بنعمله بالبيت, should be cooled at room temperature before putting it in the fridge, or if you put it hot at the freezer, what do you get? In fact نحن بنعرف الجيلو هو بالنهاية عنده two sources, يا أما animal or vegetables. So هيدي الجيلو بالنهاية في بالنهاية natural proteins يا natural polymers يا proteins يا polysaccharides. So نحن بس نطبخ الجيلو نحطها على نار سخنة، هودي البوليمر تشينز هن بالسيستم موزعين مش قراب على بعضهم منهم connected. So نحن لنحصل على جيلو منيح لازم نتركه يسقع at room temperature لنعطي وقت لهودي البوليمر تشينز يقربوا حد بعضهم enough ويعملوا cross links بين بعضهم ويعملوا imbibing لwater molecules بنصهم ليصير في عندي formation لهيدا الجل اللي بعرفه اللي هو الجيلو. نحن إذا أخذنا الجيلو طبخناه ودغري وديناه على الفريزر حيتلج المي لواحد والبوليمر تشينز حيصيروا فريزد والبلوكت مع المي المتلجة وما حيقربوا على بعضهم ولا حيصير في عندي formation للجيلو. That's why I need to cool it at room temperature before putting in the fridge. Also, I don't know if you have asked yourself about the bread, for example. مين منكم بيعرف ليش البريد بيعفن؟ For example بالنهاية إذا بدنا نحكي عن البريد يعني طحين والطحين يعني ستارش والستارش يعني عندي polymer chains. So أنا لما طبخته لهيدا الخبز وتركته يسقع وصار في عندي cross links between البوليمر chains وفي عندي water molecules. هيدا between البوليمر chains هيدا الووتر هو داخل بانتراكشنز. اذا بتتذكروا قلنا في عندي functional groups لازم يكونوا موجودين بالبوليمر chain to be able to form the network. هولي functional groups بيساهموا انه يصير في الانتركونكشن between البوليمر chains. Also هن responsible عن ability to imbibe water between the polymer chains اللي كمان بيعملوا hydrogen bonds مع الفانكشنال جروبس الموجودين بالبوليمر chains. هون if I consider الستارش بالنهاية عندي OH group. So هودي البوليمر chains مع الوقت بدهم يضلوا يحاولوا يقربوا لحد بعضهم. كل هدفهم بحبوا بعضهم بدوا يقربوا حد بعضهم. So لما يقربوا هولي البوليمر chains حد بعضهم شو بده يصير بهيدا الووتر اللي هو عامل interactions inside or between the polymer chains حيصير leaked out. بس يطلع هيدا الووتر من البوليمر chains ويصير برا صار free. صرت عم بحكي عن free water. هيدا الفري water once ظهر لبرا وبطل connected مع البوليمر chains once صار 3 صار هو excellent support for microorganisms. عشان هيك صار الخبز بعفن. Okay, thank you, see you next time.